The second lesson in our thermochemistry unit is on quantifying heat, in other words, being able to measure how much heat a substance would absorb or release in a process. 3 learning targets that we'll hit up here. The first of which, we want to be able to discuss factors that determine the amount of heat transferred during temperature change. So just asking the simple question, how much heat? It turns out that the quantity of heat transferred to or from an object when its temperature changes depends on 3 factors. The first factor is the quantity of the material, or how much is present. Just consider this. If we had a puddle of water versus an ocean of water, and we were going to raise the temperature of these 2 bodies of water the same amount, say they were going to both go up by 5 degrees Celsius, it would take an extreme amount of energy to change the temperature of the ocean, of all the water in the ocean, whereas it would take much less energy to change the temperature of the puddle of the water the same amount. So we can see that the amount of material will determine in part how much heat is required. The second factor is the size of the temperature change. Consider this. If we had, say, the same puddle of water, it would take less energy to get the puddle of water to decrease by 1 degree Celsius as it would get it to decrease by 10 degrees Celsius. So the amount of temperature change, or the magnitude of the temperature change, determines in part how much heat is required. The final factor that will determine how much heat is required to be transferred to or from an object is the identity of the material that is changing temperature, or gaining or losing the heat. Consider this. If we had rubber and steel, these 2 are different substances, and it would take more energy to change the temperature of the rubber, as I think we are pretty familiar with. Metals, such as steel, do not take much energy to get them to change temperature, whereas plastics and rubbers would take a lot more. So the identity of the material also determines how much energy would be required. Our next learning target, we want to define the term specific heat and explain its role in the change in temperature of a substance. The specific heat capacity, or what is much more commonly just called specific heat, it is the quantity of heat that is required to raise the temperature of 1 gram of a substance by 1 Kelvin, which is the same as 1 degree Celsius. Now, the temperature unit that we will use most of the time in this class is Celsius. We will use the Kelvin temperature unit in a later unit of study, but they're actually one and the same. If we increase the temperature by 1 Kelvin, that's the exact same as increasing by 1 degree Celsius. The units on this specific heat, or specific heat capacity, again they are the same thing, are the units joules per gram degree Celsius, assuming that the energy unit we're using would be joules. It could also be in calories per gram degree Celsius. It could be kilojoules, could be kilocalories, but this is the most common unit. Here are some specific heats just randomly that I've chosen to put up here. The only specific heat value that you need to memorize is this first value here, and that is for liquid water. Now, one thing to note here is we already know these values. Notice we have 4.184 joules per gram degree Celsius, which is equal to 1 calorie per gram degree Celsius. The reason why that is the calorie is actually defined this way. The definition of how much energy a calorie is defined as how much energy it takes to change the temperature of 1 gram of water by 1 degree Celsius. So that's why it works out like this. Any other specific heat you would either be given in the text of a problem, or you'd be able to look it up on a table. This is the only one you need to memorize. As we just take a look at these, we'll notice that aluminum and iron, which are both metals, have a much lower specific heat than water does. And notice these are in joules per gram degree Celsius. So the specific heat of these metals is much lower. That means it doesn't take as much energy to change their temperature. Notice the fourth one listed here is also for water, but it is for solid water, or ice. And notice it has a great effect on its specific heat. The specific heat of ice is roughly half that of the specific heat of liquid water. So the physical state does in fact play a role. Now as we look at these, you'll notice that aluminum and iron, there aren't any physical states given here. If there aren't any, we can simply assume that is for the most common physical state, which would be for a solid, obviously, for aluminum and iron. And here we have wood. Now obviously there are all different types of wood, so the type of wood probably has some effect on the specific heat. And you notice there aren't as many sig figs here for this listed value. That's probably the case. But in general, we can see that wood would have a higher specific heat than aluminum or iron or other metals would probably have. To understand specific heat or specific heat capacity, I think it's best looked at like this. If a substance has a larger specific heat, it must gain or lose more energy to achieve the same temperature change as the same amount of a substance with a smaller specific heat. So the smaller the specific heat, the less energy it takes in order to achieve that same temperature change. So it wouldn't take as long if you have a smaller specific heat. Here is a graph that demonstrates the idea of specific heat. What is being graphed here is the temperature of two substances, in this case aluminum and water, versus the amount of heat that is added. And we can see as we add energy to the substances, the temperature of the aluminum changes much more quickly than the temperature of the water. And this is because aluminum has a much lower specific heat than water. In fact, if we were to measure the slopes of these two lines, we would be able to determine how many times greater water's specific heat is than aluminum if we just compared the slopes here. Our last learning target. We want to be able to use the heat equation to calculate unknown variables during the change in temperature of a substance. The heat equation for temperature change looks like this. The equation is Q equals M delta T C, where Q is the amount of heat that is transferred to or from the substance, so Q means heat. M is the mass of the substance. Recall we said that the amount of material will determine how much energy is required, and that comes from the mass. Delta T, that is the change in temperature of the substance. And anytime we do the change in temperature or change in any variable for that matter, it is always the final quantity, so the final temperature minus the initial temperature, or what we might write as TF minus TI. So we don't just put the larger temperature first. We take the final temperature, whatever that is, and we subtract the initial temperature. And then the capital letter C is the specific heat of the substance. We use this equation anytime we have a substance that is changing temperature. Later on in this unit, we will have a different equation for heat whenever we're going through a phase change, and in that case the temperature does not change. But for now, this is what we will use because we'll always be dealing with changes in temperature. So here's an example of when we would use this equation. We are asked to calculate the heat gained by a 10-gram sample of copper when its temperature is raised from 25 degrees Celsius to 325 degrees Celsius. The specific heat of copper is 0.385 joules per gram degree Celsius. So we're going to use that equation we just presented, Q equals M delta Tc. The reason I know how to use that is because we are changing temperature, so that tells us we should use this equation. Notice the equation is already solved for Q, heat, which is what we're asked to find. So we don't need to change the equation any. We simply need to substitute in our values. So M is the mass, and that's the 10.0 grams. Delta T, that's the temperature change. That's the final temperature minus the initial, so 325 degrees Celsius minus 25 degrees Celsius. And then C, that is the specific heat. Now I always like to solve the temperature change before I worry about getting an answer. So if I take 325 minus 25, that gives me 300. Now notice there is a decimal point that I've placed here after the last 0 and 300. That's because both of these temperature measurements are significant to the ones place. So this value should also be significant to the ones place. So I put a decimal point there to indicate that. At this point I can just calculate by plugging into my calculator. And my calculator will tell me 1160. Now notice that is 3 sig figs. The mass, the temperature change, and the specific heat all have 3 sig figs, so I've rounded that to 3 sig figs. And then we should check our units. If I just look at the units here, I have grams times degrees Celsius times joules per gram degrees Celsius, and I'm showing that down here. And if we look at what units cancel, grams cancel, as do degrees Celsius, and we are left in joules, which makes sense because that is a unit of energy. Next question. Determine the amount of energy that 325 grams of water must release when changing temperature from 22 degrees Celsius to 3 degrees Celsius. Same type of problem we just had. We have a temperature change and we're asked to find the amount of energy or heat that is involved. In this case, we're releasing heat, but we're still finding Q. And the equation is already solved for that, so I don't need to do any algebra. I'm going to substitute in values here. We have 325 grams for the mass. Again, delta T, that is the final minus the initial temperature. So notice here, the final temperature of 3 degrees Celsius is lower than the initial temperature of 22 degrees Celsius. That's fine. And then the specific heat of water is 4.184 joules per gram degree Celsius. You could also put 1 calorie per gram degree Celsius because it doesn't ask us for any particular unit of energy. When I take 3 minus 22, that gives me negative 19. It's fine that the change in temperature is negative. It should be here because the temperature is going down. That would, by definition, make the change in temperature negative. When I plug this into my calculator, I'm going to round to 2 sig figs because my change in temperature only is 2 sig figs. And that would round to negative 26,000 joules, or that would be negative 26 kilojoules. There's 1,000 joules and a kilojoule, so let's divide it by 1,000. If I check my units, this is the same situation we had on the last problem. Grams and degrees Celsius both cancel. We're left with joules. Now let's talk about this negative sign here and what that tells us. The sign conventions, in other words, the rules that we follow for understanding what the signs mean, are as follows. If Q is greater than 0, like we saw in the last problem, that means energy is added to the system, or our system is absorbing energy. That makes the process endothermic. If Q is less than 0, like it is in this problem, negative 26,000 joules, that means energy is being removed from the system, or the system is releasing energy. That makes it exothermic. Another problem. We are told a 1.20 kilogram gold bar at a temperature of 20 degrees Celsius is heated. If 1250 joules of energy are added to the bar, what is the temperature of the gold after heating? And we are told that the specific heat of gold is 0.129 joules per gram degrees Celsius. So notice in this problem we do have a temperature change because we're asked what the temperature is after heating. So we're going to use the same equation, Q equals m delta Tc. However, we're not asked to find Q. In fact, we already know that. We're told that 1250 joules of energy are added to the bar. So that is Q. What we are asked to find is the temperature after heating. So we need to find TF, the final temperature. Well, I'm going to solve this equation for delta T. That will help me find the change in temperature, which will then allow us to find the final temperature. So to solve for delta T, we would just divide both sides by MC. And if we do that, M and C would cancel from the left side, and we have Q divided by MC. And that's how we get this, delta T equals Q over MC. At this point, we can substitute in our values. So Q, again, that's the heat that is absorbed or released, or the energy, however you want to think about it. That is 1250 joules. The mass of the gold is 1200 grams. Now notice I'm writing this in grams because our mass unit on the specific heat is also in grams. If I left this as 1.2 kilograms, that wouldn't work very well. And then C, the specific heat, I've just plugged in the value given to us there. So now we can plug it in our calculator, and you can see the units cancel to leave us with degrees Celsius. So the change in temperature is 8.07 degrees Celsius. 3 sig figs there because our energy is 3 sig figs, the specific heat is 3 sig figs. Notice the initial mass, 1.20 kilograms, that is also 3 sig figs. I suppose I should have a line over this first zero here in the 1200 grams to show that's significant. But we do get 3 sig figs there. Now note, this is not the final answer. Delta T is the change in temperature. We're asked to find the temperature after we heated it. So we still need to find the final temperature. The fact that delta T is positive, that tells us that the temperature increased. So we know the initial temperature was 20 degrees Celsius. We add the change of 8.07 because the temperature went up, and that gives us 28 degrees Celsius. I say 28 because our temperature only goes to the ones place, the initial temperature, so I round that to the ones place, 28 degrees Celsius. That concludes the content of this lesson. There are some review questions that I would encourage you to take a look at here. As always, I would listen to the question or read the question, try to formulate your answer or come up with a solution, and then view the solution as I have given it to you. Question 1. What 3 quantities affect the amount of energy added or removed from a substance during a temperature change? The quantities are the quantity of the substance, the magnitude of the temperature change, and the identity of the substance. These are what determine the amount of heat added or removed during a temperature change. Question 2. What are the units on a specific heat? The units are joules per gram degree Celsius. You might also see calories per gram degree Celsius, especially if you're looking at an older resource. That would also be an acceptable unit for the specific heat. Question 3. You place 2 1 kilogram cubes, one made of aluminum, one made of plastic, that are room temperature in a freezer at 0 degrees Celsius. Which cube will reach thermal equilibrium with the freezer first? Explain. The aluminum will reach thermal equilibrium, or 0 degrees Celsius, with the freezer first. This is because the specific heat of aluminum is less than the specific heat of plastic. The aluminum will not need to lose as much energy to achieve the same temperature change as the plastic. Thus, it will reach thermal equilibrium faster than the plastic does. Question 4. A block of ice, which has a specific heat of 2.06 joules per gram degree Celsius, releases 1.2 kilojoules of heat energy and undergoes a temperature change from 0.0 degrees Celsius to negative 8.2 degrees Celsius. Determine the mass of the block. So in this problem, we'd want to start with our change in temperature equation for heat. Q equals m delta T C. But we're asked to find the mass. So I'm going to solve this equation for mass, lowercase m. So I would simply divide both sides by delta T C, and that would give us m equals q over delta T C. At this point, I can substitute in the values given to us in the question. So Q, that is the heat, and it's going to be negative 1200 joules. It's negative because we're releasing energy, we're releasing heat. It's exothermic, so Q should be negative. Notice I've written 1200 joules here instead of 1.2 kilojoules because the units on our specific heat are in joules per gram degree Celsius, not kilojoules. The change in temperature delta T, that is the final minus the initial temperature, so negative 8.2, that's the final temperature, minus 0 degrees Celsius, and then times the specific heat which we are given. And I just realized I put in the wrong value there. It should be 2.06, not 2.02. That's my fault. And then the temperature change delta T would be 8.2, or excuse me, negative 8.2 minus 0, which is negative 8.2 degrees Celsius. So we can calculate and check our units. Notice all the units cancel with the exception of grams, and that should be the case because we're trying to find a mass. And this gives us 72 grams. Again, that might be slightly different if this is 2.06. I'm not sure exactly what we get there. It looks like I plugged in the wrong value. So we get 72 grams. Number 5. A 237 gram piece of an unknown metal absorbs 853 joules of heat. This heat causes the temperature of the metal to change by 12.2 degrees Celsius. Determine the specific heat of the metal. Again, we'll use the same heat equation that we've been using because we have a change in temperature. But this time we're trying to find specific heat. So I want to solve it for C. So I'm just going to divide both sides by m delta T. And that would give us C, the specific heat, equals Q over delta T times the mass. At this point we can substitute in our numbers. So Q, the heat or the energy that's absorbed, is 853 joules. We're simply told the change in temperature. Notice we're not given a final or an initial temperature here. That's fine because we're told that the temperature changes by 12.2 degrees Celsius. So that is delta T. And then we are given the mass of 237 grams. We can simply calculate, and that would give us 0.295. And notice here our units, none of them cancel, and we are left with joules per gram degrees Celsius, which those are the units on a specific heat, so that works out just fine.